Alright, so problem 7 is really just asking you to compare the frictional force in each case. And in order to understand the frictional force in either situation, you have to find the normal force. So let's take a look at each situation by drawing a free body diagram, and then by looking at what the normal force is, we should be able to figure out when is friction more or less. So if I say situation, I'm not going to write system because it's not really a system, it's the same block. So say situation A. Then the way that the forces are arranged, you have the external force going this way. There's going to be some friction back, some support from the same surface that supplies friction. Let's call it N sub A because this is going to be a different situation. And then the weight of the object, which we can just go ahead and call it mg, as if the mass of the object was m, and then the acceleration due to gravity is g. Okay, so for this one, it's easy to see the normal force is going to be equal to the weight, and this applied force it would be equal to friction if this object were moving with constant velocity. But we don't know that, and we don't really care. We're asking when is there more friction, essentially. Okay, something that I have to then do is consider situation B. Situation B, things are different. The weight force is still going to be down, and the weight force is going to be the same. Actually, I'm going to draw that on this side. But this applied force is pulling the object up the ramp, and there is an angle to the surface. So because there is an angle to the surface, which would be down here, what we're going to need to do is figure out how much of the weight is going to be into the ramp or parallel to the surface versus how much of the weight is going to be down the ramp, or sorry, before I should have said perpendicular. Now I mean parallel down. So let's do that. Let's figure out what part of this weight force is going to be perpendicular and what part of this weight force is going to be parallel. Yes, I did say fart. You're welcome. All right, now this angle is going to go right here. And that's going to make the perpendicular part of the weight force equal to mg, or the magnitude of the weight, times cosine of theta. And it's cosine of theta because theta is adjacent to this component. Okay, then there's going to be friction. In this case, friction is going to be down the ramp because that's where the external force is in the direction up. So friction would be down, and then there would also be some normal force of support, and I'll say this B because the situation would be right here. Now, the normal force and the perpendicular component of the weight force, this guy right here, they're going to be equal to each other, which, again, that means that this object is not accelerating through the surface or off of the surface, up, as if it was levitating. It's like saying the sum of the forces, in this case we would call those perpendicular to the surface, they add up to 0. So the normal force, we'll say that's the up force, B minus the weight part that is perpendicular equals 0. So that's just like saying the normal force is equal to the perpendicular component of the weight force. And we also know that this normal force is equal to mg cosine theta. Okay, so why do we care about this? Well, in situation A, the normal force is equal to mg. In situation B, the normal force is mg cosine theta. So this helps us think about what friction is going to be, because we actually have an equation for friction, and that's the coefficient of friction times the normal force. So mu is going to be the same in both situations because it says that it is the same steel plate that is in each situation, and the steel plate has a certain surface, and the surface is not changing in either situation. So mu is the same, it's shared, and what we're thinking about is that in situation A, let's call this friction A, and let's call this friction B. In situation A, you're going to have that coefficient of friction mu times the normal force, which in situation A is just going to be mg. So mu mg is going to be the frictional force. In situation B, however, the frictional force is going to be mu times normal force B, and normal force B is actually mg cosine of theta. Now, the thing about cosine of theta is that cosine of 0 is going to be 1, and then cosine of 90 degrees is actually going to be 0. So as cosine sort of increases, or theta increases, then the cosine component gets smaller and smaller and smaller and smaller until it's nothing. So cosine of theta, in this case, seeing how it's in the first quadrant, is going to be something less than 1. So that helps me to clearly see that in this situation here, this is going to be less in the inclined case. So the inclined case is going to have less frictional force, option C.